Today we're going to talk about simple harmonic motion, only this time we're going to add some vertical and horizontal shifts. So if I look at my two functions, the two things that I'm adding, you see my b value is factored out, but I have an h in with the independent variable. That's a horizontal shift, and my k is my midline shift, which is the vertical shift on the outside. So the vertical shift, that's going to represent the average value of the function. And that's the value where the amplitude shifts above and below. So if I were to just sketch a little graph of that, instead of being centered on the 0 line, we would have some kind of a midline shift, either above or below that. And it represents the average value, while the amplitude has the function oscillate around that value. Now the horizontal shift, that is just indicates the position of the function when time is 0. So where that will come into play, if you have a function that doesn't start in the middle or at max or min at t0, then you want to apply a phase shift so you can obtain either the standard sine curve or the standard cosine curve, or a reflection of those two. So we're going to see this when we model the hours of daylight, which is what we're going to do in class once we get through these notes. And you'll see it doesn't happen often. There aren't a lot of models of this because, you know, ideally you can arbitrarily choose when time is 0, but we will do a couple of cases. So one of the most classic examples in pre-calculus is modeling a Ferris wheel. The height of a person riding a Ferris wheel relative to ground using a trig function. So I'm going to walk you through one of these examples, and we'll do some more in class. Once you get it, it really isn't that difficult. There's only a few things you need to find, and once you understand the gist of it, it's pretty easy to put the pieces together. So we have a Ferris wheel that has a diameter of 60 feet, so that's probably important, and the bottom of the wheel passes 3 feet above the ground. If the Ferris wheel makes one complete revolution every 20 seconds, find an equation that gives the height above the ground of a person on the Ferris wheel as a function of time. So think about the person on the Ferris wheel. When he first gets on, he's at the lowest point. And then as he rides it, he reaches the top point, and then as he comes back around again, he's at the low point again. So what function, if this is time 0 when he gets on, think to yourself, what function would best model this? Now remember, we're not starting at the origin. We have some kind of midline in here, and we also have some kind of offset from the ground. So if you look at that and think of our curves, the sine curve starts in the middle and ends in the middle. That's not what we have. The cosine curve starts at max and ends at max. Well, we almost have that, only we have a reflection of it. We start at min and end at min. So usually we're going to choose a reflected cosine curve for Ferris wheel problems. If we get on at the bottom and time 0 starts at the bottom, which normal Ferris wheels do, that's what we're going to have. So I'm going to make a rough sketch of my Ferris wheel. Here's the circle. Here's the center of the Ferris wheel. And I know that I have a 3 feet offset from ground. And then if you think about this distance here, if the diameter is 60, I have a radius of 30. I'm going to fix that before I start to write 60. My radius is 30. As the person goes around, there's a fixed point that isn't moving, and it's the center of the Ferris wheel. So as he reaches max and min, the average, or the center point, is going to be the distance from the ground to the center of the Ferris wheel. So my model looks like this. Y is equal to the amplitude times the cosine. We're not going to do any phase shift yet because we're going to start time at 0. Cosine of bt, and then plus some kind of midline shift. We do have a midline shift. Okay, so we're going to start here with the midline shift. It's the distance from the ground to the center of the Ferris wheel, because that's the point that's not moving when we go around. So that looks like it's going to be 33. K is 33. And then if you think about the amplitude is the distance from the middle to max, or middle to min. Well, if you look, the amplitude is basically the radius of the Ferris wheel. So that's 30. Now we are going to have a reflection, so we want to put a negative sign in front. So I have the midline shift, I have A, and I know it's going to be negative. Now all I need to find is my coefficient in front of my independent variable. Well, if you look, we make one complete revolution every 20 seconds. So I start down here, and 20 seconds later I'm back where I started. That means my period length is 20 seconds. So if I'm going to find the B value, it's 2 pi divided by whatever the period length is. So this ends up being pi over 10. Now all you have to do is put everything together for your final answer. Y is equal to negative 30, because it's a reflected cosine curve, times pi over 10t plus 33. And that's all there is to it. You have to remember the average, the midline shift for the Ferris wheel, is the distance from the ground to the center. The amplitude is the radius of the Ferris wheel. And you get your B value by looking at how long it takes to make one revolution around. Okay, so now we're just going to interpret an already given function. And here it is. I have in a predator-prey model, the predator population is modeled by 900 cosine times 2t, and then we have a midline shift again of 8,000. T is measured in years this time. So I just want to answer some of these questions here. The first one is, what is the average population? Well, again, we have a midline. So if we think about this, my midline is 8,000, and that's where the average is. And I'm going to go 900 above and 900 below that. So this is 8.9, and this is going to be 7.1. The cosine curve, if I did a quick sketch of this, starts at max and then decreases and ends up at max again. So we're going to get some information from this. The average value is the midline. So the average value for this population is 8,000. The maximum population is going to be the average plus the amplitude, because if you look at it over here, it's going to be 8,900. And then we want to know the length of time between successive periods of maximum population. So I'm looking for the period length. Okay? All I have is the coefficient, which is 2, so that's my B value. In order to get the period, I take 2 pi and I divide by that 2. So the length of time is pi years. Well, pi is approximately 3.14, so it takes approximately 3 years for the population to return to where it was before, return to max. So the next example we're going to deal with in class, because it's pretty cool and it takes some time, and I want to do this with you. And this example is the number of the hours of daylight throughout the year. It is a periodic function, so we're going to figure it out. It's going to have both a phase shift and a vertical shift to it, so we will be working on that together. Finally, we're going to do one where we're writing an equation. Now, I tell you it's the sine function, so that forces you to have to use a phase shift if it doesn't start in the middle. So here's my graph. You can see my values down here. So every 2 tick marks is a unit. Here, every 1 tick mark is a unit. I'm going to sketch in my midline. So the average value is at 2. I know K is 2. The other thing you need to read is the amplitude. So if I go from 2 and I go up to max, my max is 3, so my amplitude is going to be 1. I have a phase shift I have to figure out. So normally the sine curve starts in the center and ends in the center. This one is not starting there. So you find out where's the normal start for the sine curve. And it's at 1/2 instead of at 1, or instead of at 0. Okay, because this is a unit of 1 here, and there's 2 and 4 and 3. Okay, so When I'm at 1/2, I'm starting at this midpoint and I'm increasing, just like the normal sine curve does. Since I'm moving to the right, that's going to be a negative phase. So my phase is going to be negative 0.5 because I'm moving to the right. So when you put it in, now your function, if you think of the minus h, that's going to take care of the negative 0.5. So you just got to read it like you read a regular transformation. You're moving 5 to the right. Up to, and an amplitude of 1. Now we just need the period length. So if I look at successive mins or max or middles, I start at min and I end at min 2 units later. So the period length, or the b value, is going to be 2 pi divided by 2. So that's pi. Pulling this all together, you get y is equal to, my amplitude is 1, so I don't have to show it, times the sine. My b value is pi. It's going to be factored out. T minus 0.5, because it's 5 units to the right, plus 2. So we will be practicing that in class as well. In this lesson you do your writing functions, your reading functions, and then your interpreting functions, all in one thing, so it's pretty good.